A gas giant is orbiting halfway between two stars, on a path current formation models say should not exist. Astronomers detected Nu Octantis ob through radial velocity. Its star repeatedly moves toward and away from Earth. It takes about 404 days to orbit, at 1.24 astronomical units from Nu Octantis A. Only a retrograde orbit moving opposite the binary's motion remains stable. A prograde path moves with it. Strong gravitational perturbations would make that orbit highly unstable. As it became a red giant, then a white dwarf, it lost most of its original mass. That mass loss weakened the system's gravity and reshaped the orbits. One hypothesis says planets orbiting both stars were scattered after mass loss, sending one inward onto the retrograde path. The other proposes an accretion disk, a disk of lost stellar material formed the planet later. Its exact history remains uncertain, but both explanations connect this impossible-looking orbit to the companion's transformation. Voyager 1 crossed the Solar System's termination shock in 2004, about 94 astronomical units from the Sun. Yet its instruments missed the expected local peak of anomalous cosmic rays. These particles begin as neutral atoms drifting in from interstellar space. Ionization strips away their electrons, letting the solar wind carry them outward. Models expected the termination shock to accelerate these picked-up ions strongly, creating a concentrated source near the crossing. It is a transition in the solar wind, not a solid wall. Voyager 1 did not find the local surge there, while later measurements showed acceleration continued in the heliosphere, the region beyond the shock. Voyager 2 crossed at about 83.7 astronomical units in 2007, adding a second route through this environment. Observations and modeling supported a blunt, asymmetric shock. Acceleration works more efficiently along its flanks than near its nose. As each Voyager moved farther into the heliosphere, the anomalous-cosmic-ray spectrum progressively unfolded, matching that prediction. Geologist E. Dale Jackson used Jello to model Hawaiian island formation. Years later, he co-led deep-sea drilling across the volcanic chain. The theory was simple but testable. The Pacific plate moved across a relatively fixed hotspot, a deep source of magma. As the plate shifted, volcanoes formed a trail. After leaving NASA, Jackson studied the oceanic crust and mantle around Hawaii. He used Jello while investigating basaltic magma, the molten rock linked to Hawaii's volcanoes. The desert modeled only part of the problem, not the entire geological process. In 1977, Jackson co-led deep-sea drilling project Leg 55 across the Hawaiian Emperor Seamount chain. The expedition drilled the underwater volcanoes, turning the model's prediction into a test of rocks beneath the ocean. Its geological results supported the hotspot theory. The Pacific plate had moved over Hawaii's hotspot. Jello offered a small physical model. Drilling supplied evidence from the enormous chain itself. Papua New Guinea went from absorbing more greenhouse gases than it produced in 2000 to emitting more than it absorbed by 2015. A carbon sink is a system that absorbs more greenhouse gases than it releases. In 2000, Papua New Guinea absorbed about 14,179 billion grams of carbon dioxide equivalent beyond its own production. The shift came mainly through land use change, and forestry. Those changes reduced how much carbon the country's extensive forests absorbed, but the available account does not identify every activity involved. By 2015, the national balance was about 15,193 billion grams of net carbon dioxide equivalent emissions. The energy sector was the largest source, producing about 11,806 billion grams. Papua New Guinea has committed under the Paris Agreement to become carbon neutral by 2050. That means reaching a national balance between greenhouse gases released and removed, measured across the country in its accounts. Andrey Zaliznyak created language problems that people could solve without knowing the language first. The solver reconstructed grammar from clues, not translation. Each problem supplied limited linguistic evidence such as paired forms or sentences. Solvers compared recurring changes and inferred what those changes meant. No dictionary or previous familiarity was required, the evidence itself supplied the comparison. This method reflected Zaliznyak's wider work on morphology, the study of how words change form. He formalized Russian forms into patterns. Those patterns could then be analyzed systematically. His linguistic problems therefore tested structural reasoning rather than vocabulary recall. In 1977, his grammatical dictionary contained about 110,000 words. Each entry recorded precise grammatical characteristics, turning the pattern-based approach into a large reference work. The work provided a full overview of Russian words with precise grammar characteristics. He applied the same evidence-led discipline to Novgorod birchbark letters. Zaliznyak corrected readings and deciphered several letters that had previously resisted interpretation. A machine learning leaf database contains 3 images of Photinia pagei, an extinct rose relative not as decoration, but as labeled fossil evidence. Photinia pagei lived in the early Eocene and is known from fossil leaves in northern Washington and central British Columbia. It belongs to Rosaceae, the rose family, and is related to modern Photinia species. The database combined cleared or X-rayed modern leaves with selected fossils whose plant family placement was confirmed. That gave people and machine learning systems a controlled set for comparison rather than a random image collection. The fossils therefore added verified leaf forms from deep time, not merely rare pictures. 3 specimens connected a living recognition task with a plant lineage absent for about 50 million years. That curated pairing helps humans and algorithms associate visible leaf form with plant families while keeping the comparison tied to confirmed specimens. The comparison spans modern and fossil records. Fewer than 150 people had been diagnosed with Meyer-Gorlin syndrome by 2024, yet clinicians recognize a 3-part pattern: restricted growth, underdeveloped kneecaps, and underdeveloped ears. The pattern begins before and after birth with growth deficiency. Kneecaps may be absent or unusually small, adding a skeletal clue. Both ears are underdeveloped. The same syndrome can arise from mutations in different genes. These genes affect proteins that prepare cells to copy DNA, so disrupted replication machinery can restrict growth. When those characteristic signs appear together, clinicians can order genetic testing. A confirmed result connects the physical pattern to a specific molecular cause, even in an exceptionally small patient group. There is no cure, but care can target growth, hearing, knee function, feeding, and pulmonary problems. Rarity does not erase the pattern, it makes careful recognition especially important for each person and their families, guiding diagnosis and support. A 17th-century travelogue described the noises of 2 unexpected animals, the 3-toed sloth and the hedgehog fish. Its author, Caspar Schmalkalden, was a German traveler serving as a soldier in Dutch service. His journeys carried him through South America and Asia, where observations entered a record built from travel. After returning in 1652, he assembled nearly 500 handwritten pages. They covered geography, people, plants, and animals, turning movement across distant regions into a structured account. The animal notes preserve biological observations inside that travel record. Instead of only naming species, the manuscript also captured attributed noises, including those linked to the sloth and hedgehog fish. That makes the manuscript a valuable addition to contemporary historical sources. It revealed no new discoveries from a European perspective. Yet its 489 handwritten pages still preserve what one traveler recorded about animal life across the regions he visited.